السلام عليكم طلاب. اليوم راح نبدي محاضرتنا الثانية بالاندستريال فارماسي اللي هي الميلينج. Milling is one of the basic operations required in the industrial pharmacy, one of the initial steps to formulate the final dosage form. If we want to define milling هو the mechanical process to reduce the particle size of the solid material or any material we have. The definition of milling هو the mechanical process of reducing the particle size. Thus, we increase the surface area of solids. There are different nomenclature for milling. Could be crushing, disintegration, dispersion, grinding, pulverization, depending on the equipment used and the procedure used for the process of milling. Now, milling equipments can be classified into coarse, intermediate, or fine milling according to the size of the final product, the size of the final produced particles. In industrial pharmacy, we usually express size using the term mesh, that is the number of openings in the sieve used in the screening process. And we can define particles into coarse particles, intermediate size particles, or fine particles. Thus, the milling process also can be classified according to the particle size of the final product into a coarse milling procedures or intermediate milling or fine milling. Now, for coarse milling, usually the particles have larger than 20 mesh size. Now, for intermediate milling, we have from 200 to 20 mesh size, that is 74 to 840 microns. And fine milling produces particles smaller than 200 mesh. Now, depending on the milling machine we use and the crystalline structure of the solids, we will have different size of the final products. A hammer mill may be used to prepare a 16 mesh granulation and to mill a crystalline material to a 120 mesh powder. Now that's its capacity depending on the design and other procedures and other parameters which we will discuss later. Now for the pharmaceutical application, the increase of surface area per unit weight, which is known as the specific surface area, is increased by size reduction. Now, the increase of this specific surface area affects the therapeutic efficiency of many medicinal compounds, especially those with low solubility in the body fluid. How? By increasing the area of contact of solid and the dissolving fluid. Thus, we increase the rate of dissolution. One example of this is gerzovolvine, which is an antifungal medication. When first introduced, it was a coarse particle, so its absorption, which is required for the material to be in solution, so first you have to have the drug in a solution, then to be absorbed, was very little. So we had to use large amount of gerzovolvine per dose to ensure therapeutic efficacy. Now, after the introduction of milling into industrial pharmacy, gerzovolvine was reduced to a fine particles. Now, the amount of gerzovolvine required per dose was reduced by half. That means we need less amount of gerzovolvine per dose, which will be more cost effective for the pharmaceutical company, and also less hazard of the drug being discarded into the environment with stool or feces, thus encouraging resistance to this medication. Now, the reason was why this occurred, because we improved the solubility of gerzovolvine, which is a poorly soluble drug, or let's say we improved the rate of solubilization of this medication, thus we improved its absorption. Also, in the drying of wet masses, it can be facilitated by milling. Why? Because again we will increase the surface area, thus we will reduce the distance the moisture must travel within the particles to reach the outer surface. That is the distance for removing all the vapor material or the watery material to be vaporized from the material. Now it can also be used for mixing and blending of different solids. If we have coloring of the product or of the mixture, solid mixture, and the coloring material are of different size than all of the formula, then we will have a spotting defect. This can be overcome by simply milling the coloring material with the formula to a similar particle size, and this will also aid in mixing during the milling procedure. This is also same for active pharmaceutical ingredient with excipients to ensure uniformity of the dosage form and the uniformity of batch to batch. Now, lubricants used in compressed tablets and capsules function by virtue of their ability to coat the surface of the granulation or powder. A fine particle size of lubricants is essential for it to function properly. So we have to mill lubricant to a fine particle size, then it can be used effectively in the granulation process or in facilitating the flowability of powder when feeding it into the capsule shells during capsulation. Now the milling of ointments, cream and pastes provides the smooth texture and better appearance in addition to improve the physical stability. If I have an ointment with coarse particles, it will be irritating when rubbed on the skin. So I can solve this by milling the ointment with all the ingredients in it to get this smooth texture. Also, regarding the stability, by milling all the components of the ointment or cream or paste or whatever, I will ensure that the stabilizing material and all antioxidant and all other components of the formula will be distributed uniformly in the final product. Now, if we look at the size and distribution measurements, how can I assert that these particles are of this size range? I can use the microscopy, which is the first and the simplest procedure. Now for the methods for measurement and the size distribution of particles. First we have the microscopy. This is a direct method for size measurement and to accurately measure the size distribution. The lower the limits of the measured size depends on the power of the lenses. If we look at the ordinary microscope, it is used to measure particles between 0.4 to 150 microns. Now the disadvantage of microscopy, it requires skills of the operator. Especially if we are using ordinary microscope, this will require a skill and time consuming procedure, as the operator needs to measure the different particles in the field and calculate the size distribution. That is, for example, for this range, if we have many particles at 70 microns, we will have a distribution with its peak at 70 microns to tell us that most of the particles we have are in this range, are in this size, and others we have larger at the 150 microns and smaller ones at the 0.4 microns. Even if we use electronic microscope, it will still require skills from the operator, and it will be less time consuming than ordinary microscope, but nonetheless it will require taking multiple samples to ensure the accuracy and the uniformity of this measurement to all batch size. Usually microscopy is used for very small particles, that is if we have them in the nano size or for lab scale work. If we look at the second method of measurements is sieving. This is the most widely used method in pharmaceutical industry. Why? Because it is inexpensive, simple and rapid, with little variation between operators. Whichever the operator is, it can accurately give the size and the size distribution of the sample we have. Now the lower limit is 10 microns when microsieves are employed. There are more sieves depending on the size. We can lower the limit if we use sieves with smaller openings, but still for industrial scale usually 10 microns is what's being employed. Now the procedure simply involves mechanical shaking of the material through the sieves. Then the material will be retained on different sieves. We have a series of sieves. Then we weigh the material on each sieve to get the size and distribution of the particles depending on the amount of weight retained by each sieve, as only the smaller particles will be allowed to pass between the opening to the lower sieve, and the lower sieve will have a smaller opening than the previous one, and arranged like this in a series. The third method we have is the sedimentation method. Now this method can be used in size range from 1 to 200 microns. This method depends on the sedimentation rate of particles, and the sedimentation rate of particles depend on the size of these particles as expressed by Stokes' law. If we look at Stokes' law and define each part of it, we will measure d Stokes, which is the effective diameter of the particle, can be measured by this equation. The equation will depend on eta, which is the viscosity of the dispersion media, x over t, this represents the sedimentation rate, g is the gravitational constant, and p naught is the density of the particle and the medium respectively. So depending on the sedimentation rate we will calculate the diameter of the particles, because all other components will be known. The gravitational constant is known, the viscosity of the dispersion media, it will be prepared previously, so it is a known factor. The sedimentation rate, this will be measured. The gravitational constant, this is constant, and the density of both particles and the medium is also known. Usually we use a concentration that do not exceed 2%. That is, we don't add particles more than 2% to the medium. Why? To prevent the interaction between particles, so they settle independent from each other. If we have a concentrated solution, then the particles will be attached to each other, resulting in clumps, and give us a faster sedimentation rate, and this faster sedimentation rate will give us larger diameter, and this will give us a false result, because what we are measuring here is the size of particles in the dry state. We are not measuring suspension to calculate all the factors. We need to eliminate other interfering factors such as the concentration, to ensure that the results we get from sedimentation measurement is applicable to the particle size of the final product of milling. The theory of comminution or of milling. This theory describes the behavior of solid when they are under the stress during the procedure of milling. Now, if we look at the diagram here, the diagram describes the relationship between the stress applied to break the particles and the strain endured by the solid particles. We have first an initial part, which is the linear part. This linear part of the theory of comminution is presented or expressed by Hooke's law, which is stress is proportional to strain, and also by Young's modulus, that is the slope of line, a straight line, express the softness or stiffness in dynes per square centimeter. Now, what we mean by this? When we increase the stress, the strain on the particle will be increased. This is Hooke's law. While Young's law states that the slope will represent the softness or hardness of the particles, because when we have high slope, the value of slope is high, that means we need more stress to reach this point, which is called the yield point. When we have a smaller slope value, we will have a line that requires less amount of stress to reach the point which we call the yield point. The yield point is the point where the deformation begins. In the straight portion or line here, the particles holds its original size and shape. After increasing the stress, we will reach a point of deformation. This point of deformation after the yield point and the resistance is increased, we will reach what is called the irreversible deformation, plastic deformation point. Here the sample breaks. This is the point where the particles break into a smaller particle. This is the reversible portion. If we stop the stress before we reach this point, then the material will reverse back and we will have to redo the cycle of stress to strain the particle to reach it again. So we have to exceed this amount of stress in measured time to break the particles apart. Now, the area under the whole curve of the theory of comminution, this represents the crack strength, or let's say the energy of a fracture. That is the energy required to fracture the particles. Thus, it can be also an approximate measure of the strength of the material. When we have larger area under the curve, that means we have a more solid, or let's say a material that has larger strength if we compare it with another material with a smaller area under the curve between the stress and strain. Now this can be measured, this diagram can be measured using specified devices that measure stress and strain of the material or the resistance of the material, and using complex mathematical equations. Now the size reduction begins by opening of small crack that were initially present. Thus, if we have larger particles with more cracks in them, they will easily be reduced to a smaller particle size than if we have small particles with fewer cracks in them or fractures in them. Why? Because we will need more energy to initiate the cracks, new cracks in these small particles, and break them to even smaller particles. Now for any particles, there is minimal amount of energy required to break it into smaller particles. However, in the milling devices or milling equipments, the environment is not optimal to allow utilizing the minimal amount of energy to fracture the particles. The force that is required to break the particle is the force that exceeds the plastic limit, that we said the plastic deformation, the elastic limit, sorry, that is the elastic deformation of the particles. So the most efficient mills utilizes less than 1% of the energy consumed to fracture particles and create new surfaces. The rest of the energy is expended in the elastic deformation of unfractured particles. As we have said previously, if I add stress but not enough to exceed the elastic deformation, then all of this applied stress will be lost and will be transformed to a different type of material, of energy, like heat, etc. But again, I will lose all this energy because I did not exceed the elastic deformation to fracture the particles irreversibly. Second, the energy is expended or transport of the material within the milling chamber. In the milling chamber, we introduce large amount of material. So when we begin the milling process, moving this material around in the milling chamber will require energy. Also, we have a friction between particles and friction between particles and the mill. We have a huge amount of energy that will be converted into heat, also vibration and noise. Also, the insufficiency of the transmission and motor, that is the motor of the milling equipment, most of its energy will be expended in insufficient transmission to the grinding part of the milling equipment. If the force of impact does not exceed, as I have said, the elastic limit region of Hooke's law, the material is reversibly deformed or stressed. That means they will convert back to their original size. When the force is removed, the particle returns to its original condition, and the mechanical energy of stress in the deformed particles, as I have said previously, will appear into a different form, that is heat. The efficiency of the milling process depends on the nature of force and the rate of application of this force in the comminution process. Often material respond as a brittle material to fast impact and as a plastic material to slow impact. What do we mean by this? If the grinding equipment or part of the milling equipment is introducing the force in a slow manner, slowly compressing the material, then the material will most likely act as an elastic material. I want the material to be acting as a brittle material, so I can break them apart with the applied stress more forcefully. If I slowly add the pressure, then it will act as an elastic material, and I may need more stress and more time of application of this stress to ensure that I reach the yield point. Also, the greater the rate at which force is applied, the less effectively the energy is utilized. What we mean by this? If I want to produce a new surface in milliseconds, I will require 3 times the amount of energy to produce the same surface area in seconds. So if I apply this fast force at a higher rate, I will lose more amount of energy than if I were to apply this fast force at a slower rate. Okay, and this counts in pharmaceutical industry because these heavy machines in the milling process all will use a lot of energy, and energy is a cost. So this depends. If I want fast milling, that I have a tight schedule for manufacturing, then I will use more energy. If I have a more loose schedule, I have more time, I don't need to spend a lot of energy to have the same result, so I will slow down the rate of the milling equipment. Now for the energy of comminution, as we have said previously, only 1% is utilized of the energy of the milling equipment to fracture and to produce new particles. Now, so how can we calculate this 1% to ensure that we will produce the particle size required and that this milling machine will give us the required results? One of the theories explaining this, or laws explaining this, is Kick's law. Kick's law states that the energy required for size reduction of material is constant for the change in the dimension of material, irrespective of the initial dimension. What we mean that is the energy required for size reduction is proportional to the reduction ratio, that's the size of the material fed to the milling equipment divided by the size of the final product. For example, the energy required for reducing a material of specific weight from 1000 micron to 500 micron is the same as the energy required for the same material and the same weight to reduce them from 500 to 250. Why? Because we simply divide 1000 divided by 500 will give us the same ratio as dividing 500 divided by 250. Now, Kick's law assumes that the material has flaws, or let's say small cracks, distributed throughout its internal structure, and that this is independent from particular volume of that material. Now, we know that this is not true because larger particles contain larger cracks or flaws in them, but smaller particles contain less, thus we will need more energy. So Kick's law can be applied according to all experimental values have shown that Kick's law can be applied to coarse particles only. That we mean these statements that the energy required for a weight of a specific material to be reduced from 1000 micron to 500 micron is the same as the energy required from 500 to 250 is applied only for coarse material. Now, Rittinger's law states that the energy required for size reduction is proportional to the surface area. What we mean by this is that the energy required for size reduction is directly proportional to the increase in the surface area of the final product. Now, Rittinger's law or theory is applicable to brittle material, as there is minimal deformation, thus undergo rapid production of new surfaces with concomitant surface energy absorption. Now, Rittinger's law excludes all the elastic deformation that is occurred during the stress of the particles, and that is can be applied to brittle material, as there is minimal deformation and the rapid production of surfaces. Now, the milling rate The milling rate depends on the mass and the size of the particles to be milled and produced, and the time in the mill. The material that is remain in the milling chamber. It usually follows first order law. That means we have a straight line relationship between the mass of the particles and the time in the mill to the milling rate. We also have another factor, which is the rate of feed done by the operator. This also affects the process. If the rate of feeding is slow, then the product discharge is also slower, and the amount of particles of smaller size will be minimal. If the mill is choke fed, that means fast rate of feeding the material into the milling equipment, then the milling chamber will be filled with material and it will take longer time in the milling chamber. We will have smaller particles, more amount of undersized particles, but it will also require more energy and more power to produce them, and it will take more time because the discharge is embedded by the mass of material, the huge amount of material that we added at a fast rate into the milling chamber. Now if you look the type of mills, every mill consists of a feeding shot. This delivers the material to the grinding part, which is responsible for reducing the particle size, and we have the discharge shot from which the final product is delivered. The principle of operation of milling depends on direct pressure, impact from sharp blow, attrition, or cutting. Now if we look at the types of mills used in industrial pharmacy, we usually have cutters, hammer, roller, or fluid energy. Cutter here we have that will cut the particles into a smaller size. Fluid energy, I will explain it later as it's more complicated type. The roller, in which the material is introduced between two large rolling of steel to reduce the particle size, and the hammer, which consistently strike the material to reduce its particle size. Depending on the mechanism of size reduction, here we will have the cutting, which is the material is cut by means of sharp blade or blades. Compression, which is the method that the material is crushed by application of a pressure. Impact, which occurs when the material is more or less stationary and is hit by the moving object, such as the case of the hammer milling equipment. We have to apply it at a high speed, or when the moving particle strikes a stationary surface, that is the reverse. We project the material directly to a hard surface to be broken upon it. In either case, the material shattered to smaller pieces. Usually both will take place since the substance is hit by moving hammer, and the particles formed are then thrown against the casing of the machine. When the hammer hits the particles and it is then removed from the particles, it will also cause the material to move around in the crushing, or let's say the milling chamber, so it will also be thrown against the wall or the steel wall of the machine, the milling machine. Now in attrition, the material is subjected to a pressure as in compression, but the surfaces are moving relative to each other, resulting in a shear force which breaks the particles, such in case of the roller mill, in which the material undergo attrition the surfaces move relative to each other and cause pressure to the material that pass between them. Now, the general characteristics of different mills. We have the cutter and the action cutting. This usually produces product size between 20 to 80 mesh and can be used for fibrous, crude, animal and vegetable drugs, but cannot be used for friable material. Now the hammer uses the action of impact, as we have said previously, the impact from the material being stationary and hit by the hammer, and the impact of the material moved by the hammer and projected into the walls of the grinding chamber. This machine usually produces a small product size from 4 to 325 mesh. Can be used almost for all drugs except for abrasive material. That is the very hard material that causes damages to the surface, because it's when hit by the hammer will be damaged, and then when the material reflects and move against the grinding chamber, it will also cause damage to the grinding chamber. Roller, we have the attrition and compression applied together and can be used usually for soft material. Roller usually used for ointments, creams, etc. And the fluid energy, we have attrition and impact together. This can be used for very small particles and to produce small particles, and used for moderately hard and friable material, but cannot be used for soft and sticky material, while the hammer on the other hand can be used for this type of material. Now, if the milling operation is carried out so that the material is reduced to the desired size by passing once through the mill, نسمي هاي البروسيس as an open circuit milling. يعني بكل بساطة أنا أدخل الماتيريال to be milled بالميلينج equipment، وبتأثير الجرافيتي عادة يصير positioning مال الدليفري تشات إنه تكون بالlower end of the milling equipment، وتطلع من عندها الماتيريال مباشرة. مثلا تخضع لعملية الميلينج بالبروسيس وتطلع directly delivered. هاي يسميها يعني open circuit. الكلوز سيركت ميل، هاي طبعا الاوبن سيركت هي the simplest يعني خلينا نقول design of mill. الكلوز سيركت ميل هاي one in which the discharge from the milling chamber is passed through a size separation device or classifier, and the oversized particles are returned to the grinding chamber for further reduction of size. The closed circuit operation is most valuable in reduction to a fine and ultra fine size. The closed circuit بكل بساطة إنه أني البارتكلز اللي ما وصلت للsize that I desire it will be retained and delivered back to the grinding chamber. بالتالي ما راح يطلع عندي من الدليفري شات غير بس البارتكل سايز اللي أنا مقرره. طبعا أكيد بهاي البروسيس راح تتطلب وقت أكثر إلا أن تكمل كل الماتيريال، بس أنا راح أتأكد 100% إنه الماتيريال delivered from a closed circuit operation راح تكون بالبارتكل سايز والرينج that I desire. وشكرا جزيلا.